And I can take this chance to give us again the introduction for the sake of those who haven't been here in the previous time that Dima gave the talk. So this is Dima's last talk in the 12th annual lecture series in memory of Professor Dvoretzky, which has been established in 2010. It's a distinguished lecture series. I'll give a few words about Dvoretzky, and then a few words about Dima. So Professor Dvoretzky was one of the founding fathers of the Einstein Institute. He received his PhD in mathematics from the Hebrew University in 1941, under the supervision of Michael Faketer. Appointed professor of mathematics in the Hebrew University in 1951, the first alumnus to obtain a full professor position in the university. Dvoretzky was a leading analyst, probabilist, contributing to functional analysis, mathematical statistics, probability, game theory, and higher dimensional algebraic geometry. He was Dean of the Faculty of Sciences in 1955 and Vice President of the Hebrew University in 1959, founder and first director of the Institute of Advanced Studies of the Hebrew University. He's also one of the founding members of the Israeli Academy of Sciences, served as president of the Weizmann Institute of Sciences and chief scientist of the Ministry of Defense. For his many achievements, he received the Israel Prize for Exact Sciences in 1973. Now we have a few words about Professor Dmitry Dolgopyat. So Dima specializes in dynamical systems. Amongst others, he has been awarded other accomplishment has been awarded the Michael Green Prize in Dynamical Systems and the Anna Sandrine Poincaré Prize in the Anna Sandrine Poincaré Prize. In 2020, he's been elected as a foreign member of the Academia Rotia, and in 2022, he was distinguished professor of the University of Maryland. And this summer is also a plenary speaker in the ICM. So Dima's work, as I said, specializes on these dynamical systems and probability. And some of you have seen the posters for his talk with the famous Galton board. So Dima's work even has relationship with the Galton board, establishing some of the fundamental properties of this random process. I won't get again into all the details, as I gave some more details last time. Today, we'll talk about randomness of circle rotations. Thank you.
Okay, thank you so much again for the introduction. And so last time I was talking about probably most random sequences which one can have, so independent sequences or Markov sequences, but today I will discuss most regular sequences which are rotations of the circle or translation of the torus. So let me start with a definition. So the object which I'm going to study is a discrepancy. So if we have a probability space and we have a sequence of points, they can, given the number n, they can study discrepancy of a sequence is just very associated to some set omega. This is just the number of points in the set, and we subtract the expected number of points, which is n times the size of a set. So, for example, if we take Xn independent chosen in the distribution mu, then the number of points is going to have binomial distribution, and therefore discrepancy is going to satisfy central limit theorem. But what I'm going to discuss today is a different case when my space is going to be a torus and mu is going to be a Hard measure, uniform measure, varying by translations, and then I consider the transformation x and the translations x0 plus n alpha quadrilateral sequence, and we want to understand how discrepancy behaves for this sequence. So the classical result, which is called while equidistribution theorem, says that the discrepancy of rotation by alpha goes to 0 for all sets with whose boundary has 0 measure, if and only if for any continuous function is time average is equal to space average, and this is also saying that there are no resonances, so there are no integer vectors m, such that m times alpha is going to be an integer. And so this can be verified by extending the function into a Fourier series. And so basically what we want to see is the rate of equidistribution of the theorem. So if we take a typical number, we want to see how the discrepancy behaves. So one classical object which is studied in say in number theory and numerical analysis is a maximum discrepancy. So you take maximum of discrepancy in general, the maximum of discrepancy along all straight boxes, and this is related by Cox-Clark inequality. This is related to numerical analysis. So you have certain class of functions, and you want to see if you want to numerically integrate this. So you just to integrate this numerically, we just compute average along our sequence, and so this maximal discrepancy measures how the norm of a separator. So if you have a function of zero integral, we want to see the norm of a separator of taking averaging with respect to functions which have variation less one. So this is has importance.
What is the inequality?
Sorry?
Written and quality.
Written?
Is it inequality instead of equality?
So this is just for any, so this is supreme. So for any function h, this my difference is going to be less than dm star times variation of h. Variation of h. Just to say that maximum is achieved. Just to say that maximum is achieved on the box.
But not on a continuous function.
Yeah, no. This is functions of bounded relations.
What is the supremum? Okay.
Supremum overall. So we just again, so you take function. So you take sum h of sm minus
The definition of
and this is less than times the norm of h.
Just there is an N missing before we into parameters. And this is what are the restrictions on H?
H has the variation, but this varies. This norm should be bounded variation norm should be less than this one. Yes.
So this inequality applies to all functions H of bounded variation.
Yes. So here I just put variation equal to 1, just for equal to 1. That is it. This is just to say that if you want to estimate the error of this numerical approximation, you have this bound, this is on depends on the sequence, this is on the
Is it the classical variation or with the control?
yeah, this is variation is to a variation. So this is just
what is the omega box? Sorry?
sorry,
What is the omega box?
just this product representatives.
Oh,
Omega is a
omega
box.
is a box.
Yes.
Okay, so omega is of a particular time is a box.
Axis covering.
So we are going to fix in most of the talk, I will fix a box and discuss what happens with discrepancy for a fixed box, but you can also study this discrepancy. So for example, for for rotations of a circle, it was studied maybe around 100 years ago by Ostrowski and Hitchin, and then it was extended by Joseph Beck to high dimensions. So it's what is called Hitchin type theorem. So Hitchin type theorem says that for almost every alpha, this series is bounded if and only if this series 5n converges. So we have.
So it's a different system, or it's still there?
No, this is for rotation pattern.
Still.
And this is the result holds for almost every alpha if and only if we have this bounds. So and so the previous result, it deals with what happens when you allow to change n, because here you see that we have this inequality is greater than some number m, has infinite solutions even only if this series diverges. So here with change n, one can also ask what happens with this expression if what is the typical size of this expression for fixed n, and this was addressed by Kesten in 1965. He shows that for alpha being uniformly distributed in the circle, if we consider maximum discrepancy for fixed n, then it grows like with probability 1, it behaves like probability close to 1, it behaves like log n times 2 to pi squared. So this is for we take maximum over all intervals and we fix n, and then Kesten also studied the question of what happens if we fix interval. So here we take interval from 0 to a, and we assume that x and alpha is uniformly distributed on the circle. Then what we say that correct rate of growth is some constant which depends on n times log n, and after this normalization we have a convergence to Cauchy distribution. And he also showed that this constant C of L, he had an explicit formula for this constant C of L. So C of L is integral of certain function along certain for some measure, and for each L there is something measured variable for horizontal flow, and this C of L is computed as an integral of C of L along this function. In particular, if L was irrational, then the measure with respect to which you integrate would be Haar measure, and if C of L is if L is irrational, then you have certain closed for a second when you integrate the function over this. And so this was the result of Kesten 1961, and then also recently Bordel, he computed this integral for all L, and he showed that this function, this integral is in fact constant, does not for all measures which one can study. This integral has the same expression. And he also obtained some other results. If you consider the the length of interval is so is rational, then we have that if you take maximum over n less than m, so this should be n. It should be d. So we take maximum that you have tn. So maximum n less than n something, and then this maximum converges to one-sided stable random variable, so index 1. So if you have fixed interval, then you have two-sided stable law, which is Cauchy law. But if you consider maximum, you have one-sided law, and so this is again every version of Cauchy limit theorem. So the previous result was valid for all length of interval, but here the result so far is known for rational length of interval, and when it's open for irrational intervals.
Why are the two expressions different? I mean, on the max, you,
Maximum and minimum.
you ask about D minus
L is interval is fixed. So
you
you
normalize by log n, but on the left, no.
no, this is just, no, this thing is, no, just the normalization is by minus 3n. So this have this, if you take just maximum or minimum, is going to be, law is going to be symmetric, but the theorem says that you have joint distribution, where, like, you have the Cauchy theorem for each one, but it's also says that they are symmetrical.
No, but I think his question is that the two terms, they don't have apparently the
Don't
same
have
growth
the same.
rate. Because here you normalize En by log n, and on the left-hand side term, En is not normalized by log n.
Yes, sir. It should be both,
Normalized by log n.
yeah, it should be.
So the same, the expression with the max is the correct one, which
Yes.
is taken min and max.
Yeah, you should be both.
That's the correct expression.
Yeah, this one should be correct. So this is. Let's say, and so now what I want to discuss, what happens if instead of one-dimensional torus, we take high-dimensional torus, and if we take high-dimensional torus, we have several choices of what kind of sets we want to take, and so the most general conjecture is that if we take omega to be semi-algebraic set, so it's given by finite number of inequalities, then what we say with taking random translation of a random torus, we have some proper normalization, we take, we have a limited distribution. So what does it mean, random translation of a random torus? So we take the torus which we have here is going to be Rd over L. L is in the form A times Ct, and we suppose that triple A, alpha, and A have joint smooth density on the space of possible triples. So here maybe some, so this is just a statement of this conjecture. Basically, why I put this slide, because basically this like one day my daughter didn't have her in kindergarten, and so I told her I need to prepare important talk and I need and then I want to play with her. But then she said that maybe if I help you, you're going to finish it up much faster. But I said you don't know any math, and then she said, okay, but we had yesterday in kindergarten we had the math class, so she taught me some.
So instead of drawing and then drawing a semi-algebraic set.
Yeah, so when this has some sense here, and so what I asked you to do is to color the set, and so this is what she did. So she asked me to promise to put it into my slides, and of course I didn't want her to finish very quickly. So you see what these colors are different. So what I asked you to do is to first take a discrepancy of the set, you take a multiply it by indicator with alpha is different by number, and when you take a to norm, and depending on how fast a to norm grows, she power is different. So for example, if it is grows by log, obviously if the normalization is like log and square, you have real. If it is log and cube, it takes green, and yellow would be n to the power 1/4, red n to the power 1/4 log n, n to the power 1/3, and so on. So this is just to make sure that she is not going to finish very quickly. A question? No, very quickly. So this is the general conjecture, and we know it for some sets, but not for all. And for example, we don't know it for this star, or we don't know this for tetrahedron, but there are some results which we know. So if
Can I ask a stupid question?
Yes.
Why should we, I mean, we have two unrelated objects and we just assume for one object we can come up with some random translation and random torus, which grows like the rate coming from another object. What's the motivation?
Sorry?
The motivation for the conjecture that you posed.
yeah, because we have some, like I said, we have some special cases when we know that is happens, and basically it should be depending on how flat about geometry of the one, because many points can be.
So those sequences A and they're very special. So
Yeah, the sequence is let's say, but in sequence we take Fourier transform of discrepancy, we multiply it by indicator of alpha is defined by number, and then we calculate the two. So this is how we get this number. And then you have certain distribution results which you need to prove to have this. So here are some examples. So in 2014, with Bassan-Fayette, we proved that if you take real analytic set, then the dimensions, then discrepancy is going to grow like n to the power d minus 1 over 2d. So this
And densities again?
sorry?
Like x alpha and x they are density or something again?
Yeah, this x alpha and L, we have some density, small density. And yeah, so this result is weaker, for example, than casting result, because casting fixed the torus. Whereas here we want to modify the torus, and in some cases we can remove this condition and consider a fixed. Sorry for that. We have slightly weaker randomness, but we don't want to know in case we can fix the torus and fix torus with some condition. Unless we know something about the torus, like sides, for example, something about the S. So the torus will be given by rational. So this is the first result was real analytic sets with discrepancy grows like n to the power d minus 1 over 2d, and we have limiting distribution, which is kind of non-standard. And on the other hand, if we take cube dimensional space, then regularization is by log n to the power d, and limiting distribution, discussion distribution as the same as is in casting field. So, so in dynamical systems, usually you want to deal with fixed alpha, but the problem with fixed alpha is that we don't expect to have good results. So if, for example, we take one-dimensional discrepancy, then if h is a function of boundary variation, then Jacob's main equality says that if you take time qn, which is base denominator, where denominator of continued fraction, then you don't have a growth over Hercule sums, so you cannot hope to get some universal behavior by normalization. So this would not really lead to any limiting distributions. In one case, one can also show that even if you box or some convex set, then again, this limit does not exist for almost all alpha, even if one can show that limit doesn't exist for all alpha. This may be, it's not really, you can find some exception alpha, but at least for almost all alpha, we know that the remaining set of limiting distributions which one can obtain is infinite dimensional. So this is the question. We don't know if maybe there exists some exceptional alpha L when they don't exist, but we don't know. One can try to overcome this. There are several ways. One is what Kester did. He took alpha to be a random number. Another possibility would be to study all to try to classify all big limits, but this also appears quite difficult. But in any case, we want to study what if we know of the big limit, what does it tell us about arithmetic properties of alpha. So, for example, we know that all limiting distributions are atomic only if alpha is rational, but we don't know about our cases. What we know that if all limiting distributions are either atomic or not, what we want to maybe one interesting problem is suppose that all limiting distributions are either atomic or Gaussian, then we want to know what alpha is of boundary type. So there are some results about
Bounded type has to do with the
Bounded type is,
continued flux.
yeah, when there's a continued fraction expansion with alpha, which is and so when there are some result,
So you allow the A's to be both positive and negative.
sorry,
You allow the A's to be both positive and negative.
so A is it's really interesting. Very much. Out of continued fractions, what is going to be? Yes.
You always randomize with respect to some back measure, like a smooth torus, or how do you?
Yeah, so here we assume that X is uniformly distributed. When you invest to last the next results, we assume that alpha is irrational, and you consider interval from 0 to 1/2, and there is a theorem of François Levenier's 2009, and it says that we can always find the sequence Nj such that the discrepancy with proper normalization satisfies central limit theorem. So, but Nj are really, in his real examples, Nj is very sparse set, maybe to the sum of n, q, and squares. When we take some very fast growing sequence, and when we take something else. So he uses central limit theorem for super-Lagrange sequences. So this is one idea of this. When there is a result of Collins and Reborn, 2009, and it's satisfied under some different time condition. It shows that there is a subset. Maybe if AN had one, maybe it should be sufficiently small. Let's say, for example, if AN is bounded, then there is a subset of density. Sorry, when we can, if AN are bounded, then there is a subset of density 1, such that if we take all the numbers from this subset, then we have central limit theorem along the subset. So we can remove zero density subset for integers and obtain central limit theorem in this case. So another result is another approach is due to Beck 2011. So here what he does, instead of removing some set, he takes the time to be random. So what is his result say? Suppose we take alpha to be quadratic irrational, and then we will take rational A to be the length of the interval which we want to study this to be rational, and so we take n uniformly distributed from 1 to n, and now we have said if there exists some constant C alpha A, such that if we consider discrepancy, we subtract some constant times log n and divide by square root of log n, then this converges to normal distribution with some zero mean and some positive variance. But what is interesting about this result, that here, so first of all, the only random object here is time. The initial position of the orbit is 0. And what is also interesting, what we take in the definition of discrepancy, which is we subtracted the expected number, but here he still have there is still some possible bias, because if C is non-zero, then discrepancy has tendency to be more often positive, more often positive, more often negative, even for in the definition of discrepancy we subtracted. And this constant C, which we have, it can be 0 or non-zero. So here are some examples. For example, it is 0 for square root of 3, it is 0 for golden mean, but if we take square root of 2 or square root of 7, then it is not 0. And then with Arthur Oliver and Arthur Oliver we extended this result so first of all, we're allowed to have arbitrary initial condition not necessarily 0, and then the normalized constant may depend on the x, not on the and is not going to be proportional. It can fluctuate between plus and minus, or so fluctuations are what the logarithm m. And secondly, we have local limit theorem. So instead of saying that dn divided by the probability that dn belongs to interval of size square root of log m, we can control probability that dn is equal to a fixed number. So this is just a very improvement which we have. And so this is the first result, and now the result which we got with a few weeks, it says that now we can realize the answer equation when this numbers, this normalization constant is equal to 0, and now we again can still be continuous fraction expansion, but now we allow aj to be, we want to aj to be even, but we allow aj to be both positive and negative, and then we say that this coefficient c of alpha 1/2 is equal to 0 if this even continuous fraction expansion is this number of sign changes of this and k is gross something like that. So this is realistic. Whereas like we can also if L is our rational number, then one gets some expression which is more complicated because it involves more serious coding for the corresponding group. So it is may have more terms to what we have for one term.
This result is for boundary type, right?
Yeah, these results and these results are also and these results are also under modular valid for modular condition if like this result here is also valid for modular condition. We don't need alpha to be quadratic irrational. We may have alpha of bounded type, but if alpha is of bounded type, the result we should say that this condition is necessary and sufficient for what we call uniform distribution in distributions for K1, K2, cardinality of and such that 0 1/2 is equal to K1 divided by this. Is equal to K2, and that is 1. So this condition here is necessary and sufficient condition for this, but it does not imply for if a number is not quadratic irrational, but it does not imply that there are no bias in the sense that discrepancy is equally likely to be positive. It can still be with 99% of the time you have all the discrepancy to be positive, but still you can have this condition. So there is no, so there is some bias, but not really. So here are some results which are extending available theorem for larger set of numbers. So here is as we mentioned, alpha can be number of bounded type, and A is required to be of bounded type in respect to alpha. So which means that we take Q alpha minus A minus B. This is greater than C over Q. So now alpha is of bounded type if this holds for a integer, but if one can see that a integer is the same as allowing a rational integer, a change in this constant C. Therefore, this numbers, the set of numbers which are bounded type with respect to alpha is large number, larger set, but this set is in particular set has called of dimension 1, but it is not it has the zero measure, and for the set we have still the central limit theorem and local limit theorem for random discrepancy is going to hold. And when there are some questions, so again, that theorem gives central limit theorem for random for discrepancy at random time, and we want to, but we don't know precise definitive conditions for alpha for to hold, and we don't know what is optimal condition for A, but what is Bromberg Uchenbein loop, we announced that we can prove it for all if alpha is lower boundary type, when for almost every interval you have central limit for temporal central limit. And on the other hand, so this all results for lower boundary type. This is as I mentioned, surface has outdoor dimension 1 of zero measure, and we want to ask what happens to almost all alpha when if L is rational, then we will give Dvoretzky, but in this case, the set of limit possible midpoint of the normalized distribution as n becomes uniform distribution from 1 to n is infinite dimensional space, because infinite dimensional space of parameters. So you can have large set of possible distributions, and in particular, one of the key steps here in our analysis is the following. So we say if alpha is uniformly distributed and n from the torus to n is uniformly distributed from 1 to n, then discrepancy of say 0 alpha interval from 0 to 1/2 and normalized by log n converges again to Cauchy distribution. And so this, once we know once we prove this, then the proof also show if alpha is fixed, then we can find quenched linear distributions, and this quenched linear distributions is a large set. So maybe I want to say a few words about the proofs of this result. So maybe let us start with a simple result. So here I wanted to discuss so far rotations, the translation of the torus, and we have set bounded functions. So here I consider a simple problem, but I consider a function which has discontinuity, has two poles at the endpoints of the interval, so like 1 minus cosine square of 2 pi x, and we want to say that if x and alpha are uniformly distributed, then we have convergence of this, and we also want to classify to see what is the limiting distribution, and then to analyze this distribution of this term, this split of terms into two parts. So we take basically the interval from zero. So we have this circle where is the function has pole here, and we have endpoints. So closest distance, we expect the closest distance on our orbit. So we expect so the closest distance to orbit would be of order like 1/n. And so we fix some large constant r, and we split our orbits into points which are close r to n, and points which are far r to n. And for points which are far from the pole, just by taking expected value, we can see that they don't give a contribution to give small contribution to discrepancy to the sum normalized by n squared. And so if, because we have a pole of order 2, so we have the likelihood comes on the distance 1/n. Each individual term has size of order 1 n squared, and so these terms which come to this closed distance have a limit distribution. And so if the point comes close, then we can replace 1 minus cosine by the closest square of the closest distance, and then we have And so now we want to see, we take points from, we want to take this, our favorite point of the circle, which is, for example, 0, and we consider we want, we expect the closest distance will be over the 1 over n, so we consider n times the distance x distance to this point, and we want to see what is the limiting process, which we will see. And when this problem was analyzed by Jens Markov in 2000, and he proves that this process, when we take the points near 0 and replace in the scaling by n, when this converges to a limiting process, and the limiting process. So what is, so if we take n alpha plus x, the distance to the closest integer, sign distance, so we have n alpha plus x plus m for some m, and so we want to study this sequence here, and we want n over n to be less than n, which means that n over n less than 1, and so what one can restate this as follows: we take this lattice, we take standard lattice Z2, we shift it by x, 0, and then we multiply this by this matrix here. So if we multiply this, we get exactly the elements of n and alpha plus x plus n. So if we just consider this product about normalization, and then we scale this as we want, and we want to see how many points belong to this interval A1, A2. And so this seems, if we want to know how many points belong to interval A1, A2, then we can see that this is the same as number of points in this lattice, which depends on n, how many points belong to the square, to the rectangle A1, A2 times 0, 1, and what happens as n goes to infinity, alpha is uniformly distributed on unit interval, x is uniformly distributed on unit interval, then we have that this set becomes equally distributed on the space of all affine lattices, and from this we can basically see that this unit distribution is given by the sum of, we consider, so we take a lattice, we can consider random variable x of L, which is the sum of all elements in the, so we take vectors, we take the string y less than 1, and we take all points in this string, or sorry, y is 0 and 1, and we take, so now all points in our lattice, and this number of points
What is y?
Sorry, no, we take vectors e, all vectors in the lattice, and then x of e, y of e, and we consider all points such that the second coordinate belongs is between 0 and 1, and this number grows linearly, and because this number grows linearly, this series is going to converge, and so this this expression which we have is some function x of lattice. And now we take L to be uniformly distributed in the space of lattices, and if L is uniformly distributed in the space of lattices, we get sort of a random variable, and this random variable is going to be a random variable which is appears in this limiting field.
And it doesn't have any expression in terms of known distribution, it's just its own distribution.
Yeah, it is. Yeah, it is new kind of distribution, so we call this random secret transform. Yes, and sometimes you can also do, instead of one pole, you can consider two poles which are and point 1 to pole and point 0, we have a pole at point L, and now the analysis is going to be the same, but now we will have a sequence of, instead of space of affine lattices, we have a space of 2 points configurations, because we can, red points correspond how close we are to 0, and the green points current how close points which are close to the second pole, and then now we don't have if we take any 0 and L were not necessarily from distribution because, for example, if we start with green point, which is midway between two red points, then this is going to be preserved by the dynamics. So we have still we have a result by Lewis-Sharp, which is especially in the case of Ratter theorem, which says in this case we will have once we start with our original lattice and consider the images of all its all the blow-ups, then this very limiting distribution is going to exist, but this limiting distribution can be even distribution on all pairs of either is going to be distribution on the whole Harmon here, or it can be some subgroup corresponding to two lattices which are rational, which are commensurable to each other. So you can have again we can again identify the limit distribution, but the distribution depends on whatever L is rational or irrational. And maybe one to just to complete the analysis. So here we can find the same argument as in this case applies to functions which have polar order 3, 4, 5, and so on. But if you consider poles of size 1, then the corresponding sum is not going to converge. So in order to converge, you need to consider some summation method. For example, take the principal value, and so this is what C9 and Dolgopyat have. If you have a function with one pole, you still have a limiting distribution, but now this Ziegelin transform needs to be understood in as a principal value, as a summation. You take, for example, sum from minus n to n, and then you take n to infinity. So this is the limit distribution in for rotations and meromorphic functions. And just to compare it, if we consider discrepancy in Keston theorem, so the limit distribution is Cauchy distribution. So Cauchy distribution, so here in the C9 Dolgopyat theorem, we have the limit distribution is going to be the sum of 1 of xj, principal value of the sum of the sense of so xj is quasi-lattice. So projection of two-dimensional lattice. So we point two-dimensional lattice such that if one-dimensional lattice is the same order, the first and the second order is between 0 and 1. And if we want to study Cauchy distribution, it's going to be the same expression, 1 xj, but now xj here is going to be times the Poisson. So basically the expressions are very similar, but the geometry of resonances is slightly different. So this is how we can see that these two problems have the same flavor. And so to prove the results which lead to this Keston theorem, one approach one can take is to study to again identify the terms which make main contribution, but now instead of working in the phase space, we would like to work in the frequency space. We take Fourier transform and we study terms which makes contribution to like what we call small denominators, which small denominators make leading contribution to frequency. It becomes some kind of similar counting problems in the space of lattices, but it is basically involves but before taking this, before studying applying the second distribution results, we would need to do some elementary manipulations with Fourier series. So here maybe one I discussed some extensions on this, and so this was studying of circle rotation, and so now instead of taking one rotation, I want to take two different rotations, And so this is also related to what I was discussing in my first talk. So we have, so we want to study some and independent random variables. And now I suppose we independent random variables take three different values, A1, A2, and A3. And now I take some interval Z1, Z2, and I want to, and what we know is that if we consider probability as Z1, Z2, then for there is a local limit theorem which is the square root of the variance of this, so the square root of n times some expression variance of standard deviation of x, and then is length z2 minus z1, maybe some Gaussian term corresponding to z minus simplification percent, variance. So we have a leading asymptotic expression like this, and we want to see if we could find corrections to this. And so, like, if we want Sn, so Sn takes possible values of Sn would be a, so K1 plus K2, K2 plus K3, K3, where K1 plus K2, K3 equal to m. So we just want to count how many bonds we have in interval of this type and in interval Z1, Z2. But before we were counting each point with equal weight. Now we take point if we take points with weights corresponding to factorial of K1 factorial, K2 factorial, K3 factorial, K1, K2, K2, K3. So, so we assume that we formulated we assume that we have zero mean, so we don't need to worry about this term here, and we want to study the corresponding discrepancy. And so when the statement says that if you consider the local limit theorem, normalizing by some smooth function h of at, so we subtract the expected value. So I think we just go to yes, this is n here and the square root of n here. So we take the difference between left hand side and right hand side, and we multiply the square root of n. And the statement says that this converges to again certain Ziegler transform. So now again we take we take lattice and then we take a character and we consider a following sum. So we'll have a vector x called e y b in this lattice, and how we sum over all non-zero vectors in the lattice. This expression sine of the character divided by y and e to the minus x squared. And again, the sum has to be understood in the principal sense. So we just take a big ball and we consider limiters. So the sum doesn't converge absolutely, because see, if sine is greater than 1/2, you can see that there are x, when x is less than 1, the number of terms is going to be n, and so the series one of y is going to converge. So to make the sum converge, we need to take into account cancellations between numerators. But if we take this into account by considering limit as again on the square radius of sine n, then the limit exists, and so we take and results saying that so if A and P are random, so suppose we take smooth distribution of all possible values of the parameters, then and so Z is fixed. So this correction in the central limit theorem becomes now something which depends on A and B. If A and B are random, this becomes a random variable. And what we say, this random variable, after we divide by some smooth function, it becomes it has a limiting distribution, and this limiting distribution does not depend on the distribution of A and B. So which means that if we don't know A precisely, but we know A with error of say 1/10 of 1%, then we don't know anything about the correction to the central limit theorem, and this correction is given by this difference of theta A K1 and theta A K2, and then the lattice is uniformly distributed in the space of lattices and character. So now we take lattices centered with 0 before we affine lattices, and here K1, K1, K2 are characters will be chosen independently from the space of characters. So we can have correction here, and maybe just what we want to say to compare with is if so this is again the count of maybe values of so maybe value of a linear form of two variables because K3 can be correct. So K this is what K3 can be correct from K1 K2 here. So we can count the values of linear form of certain number of variables, but when we take not integral weights, but weights which are equal to binomial coefficients, then the linear distributions is given in terms of random zero transforms. But if we take a random variable with terms and we take a fraction. So this is because it's mixing two things. But one thing saying we can count fractional part of x plus n alpha divided by log n, and when we subtract n times a divided by logarithm of n to the power d, this can go to Cauchy distribution. And on the other hand, if we take n plus a1 n1 plus a2 n2 plus x, if we take the fractional part of this, then this is the same as a1 n1 plus a2 n2 plus x plus some n3, where n3 is chosen, especially if we want to hit the interval. So we can consider the same, we can remove this fractional part, but we can consider now linear forms not on d variables but d plus 1 variables. Then what we need to subtract is going to be not just linear function, but some certain polynomial which count the volume intersection of the volume of range of this form with set 0a, and then the distribution if d plus 1 variables, so to figures which we have together in this paper. But in general, what we see that there is a contrast between if you take different weights, then you have different normalization and you have different different limit distribution. In one case, it's given by classical Cauchy limit distribution. In the other case, it is given by zero transform for the space of random lattices. And I think I don't have time because I wanted to sketch also a bit of that theorem, but I think also Amri gave a talk here, like in the colloquium which he was explaining this proof. And so I don't have much time, but basically what we see with linear distributions, it involves to study linear distribution. What is useful is to study renormalizing transformation, which is acting on the space of Tori, and it's just rescale the torus by carry from the chosen matrix and using some dynamical properties, particularly unique properties of this selection. One can obtain many results about linear distributions. So recently there was some results about quantitative distribution. So hopefully there was several conclusions which I mentioned, which hopefully could be resolved in these results. But still, we have some. So far, we have some better understanding of discrepancy. See how decades ago, but we still have questions. Thank you so much for your attention.
Any questions to Dima?
What are the methods for this? Say when you have normal limit, those part of the approximations.
You need to have, you use martingale approximation, but usually for, so you consider orbit of renormalizing transformation. So maybe it is Serenos, or maybe it is particular flow, maybe it is something else. And for this particular, we use mixing. So using mixing, we have martingale composition. And to apply this theorem, so we need to verify condition, which is like the condition, which shows that each term is small compared to the sum. And this happens if the orbit doesn't come very far in the cusp. But for typical orbits, we can in the cusp, when you run this, it turns out that the easiest in the cusp, the one problem.
Is it possible to have
Strong limit theorems, but you can, but the point is that usually normalization is by log, so it will be some time change, for example, of Brownian motion, which you can control. Because this discrepancy will grow, don't grow like square root of n, they grow by some time log n, square root of log n plus hours.
Maybe I will answer the question. So in the first part, the discrepancy we consider for fixed n randomized over x with respect to Lebesgue, I guess. But okay, so the process is taken from some dynamical system, which you could conjugate by, let's say, a Helder net, and then it wouldn't necessarily preserve the Lebesgue measure, but it still preserves the intervals which generate your discrepancy. So why don't we look at other measures which are somehow relevant to this dynamical process?
Yes, this is the question. Basically, what he says, if we consider rotations, where is natural, where uniquely ergodic, so unique measure is Lebesgue measure. If you consider where are some results, where are some questions about families of, say, one parameter families of diffeomorphisms, then we need to be a little bit careful, because if you consider one parameter families of diffeomorphisms, they have rotation number is rational with false probability, rational with positive probability. So we need to take this into account. Maybe one would guess if you remove rational intervals, then condition for the rotation need to be rational, we would expect it to guessing the theorem, but I think it's not known. And also various other cases where it is known that we map singularities, for example, maps which have maps which have the flat points, maps which have breaks. If you consider parameter families of such maps, it is known that rotation number could be irrational probability 1, and for such maps, but for such maps, if you subtract the inverted measuring, you would expect maybe a central limit theorem with normalization like log n. but this are not known. What, for example, there is one result line which you want to consider, which is a student Aguma. So she studies math, representing maps from the torus. Suppose it has, say, one fixed point. And so now you consider a function which is, you suppose that your initial condition is uniformly distributed on the circular component, so it's not this. And rotation of the uniformly distributed from 0 to 1, then you have, you take phi to be C2 function, then you consider the develop phi GT dependent parameter. And so you have some liquids, subtract the develop phi, then over the component, then you expect this to behave log T square times Cauchy distribution. So, and you can also study some other examples which you can study is translation flows. Translation flows usually there is they grow phenomenon, you can do some power, but there is a coordination in the G 3G, such that you can consider functions in this coordinated G space, so you don't grow phenomenon for this function, so you can also expect this kind of testing in the field. So in principle, here we use like as I mentioned, Fourier analysis, but in our case, one is to use some different arguments. So this is our question.
But you want some Fourier decay for the measure, some property like that, that's something to expect to be sufficient, some strong Fourier decay for the measure.
So here I want to so this is a problem almost pretty you expect a question about definition. You want to see how if you do some randomization, you have different shapes, but there are some shapes where every values are not small, and basically there are certain shapes which you want to study and you want to understand how often when you move in the model space, how often you come to the space where the shape becomes small. For example, your surface is parts with small neck or something like this, and for this one is basically this. But it's important questions.
You can think, you might go. There are refreshments in the lounge room. But then I kind of lost you on where to use orbit closures. I was curious where you studied the orbit closures. Because the distribution here of fluid to orbit distribution, I don't understand how much goes to orbit closures.
Orbit closures because you take like in this case you have this approximation of efficiency, the risk is